SCRAPS was a collaboration between the University of Würzburg and the UC Irvine. But before we jump into the topic and what it's actually all about, let me start with a brief motivation. So, IoT services are constantly expanding, from smart home solutions to smart factories and even whole smart cities. And in order to realize such large-scale IoT applications, we are deploying millions of small devices everywhere throughout our daily lives. To interconnect all these devices, IoT networks often opt to use asynchronous communication, mediated by intermediary devices, so-called brokers. And as devices within large networks are usually not owned by one single entity, but by many different stakeholders, and they might be potentially malicious, we have to find a solution to detect malicious devices and also establish trust between mutually mistrusting parties. And one way to do so is to use remote attestation. But before we go into details about remote attestation, just let me give you a brief overview of pub-sub communication and its challenges. So, unlike traditional communication protocols, where the devices directly connect in order to exchange their messages, IoT networks use asynchronous communication mediated by brokers. This means the device that tries to send the message, called the publisher, sends it to a broker who then forwards the message to all the devices that registers their interest in beforehand. This registration is called a subscription, and the devices therefore subscribers. One big issue with this communication architecture is that we can potentially have malicious brokers. And as they are basically the backbone of our communication network, they are responsible to transmit every message and are capable of manipulating and altering them without the publisher or the subscriber even noticing it. With this in mind, we have to face some significant challenges when we want to apply remote attestation to such networks. The first one is we do not have any security guarantees like integrity, confidentiality, or freshness. Another issue is asynchrony itself, as publisher and subscriber cannot directly interact with one another. A third issue is especially because we are talking about IoT, small resource-constrained devices, which means we usually have very low memory capacity, we are also computationally limited, and we have very heterogeneous devices. With all these challenges in mind, now let's come to remote attestation and how it is originally designed. So, in the original design, we have one verifier and one prover. And the protocol is a challenge as response protocol initiated by the verifier by sending a random nonce to the prover, who then, as a response, calculates an attestation evidence, which is usually some kind of hash of the whole device memory. He then links the calculated evidence to the nonce and sends it back to the verifier, who then will compare the received evidence to a database of pre-known and good values. So far, so good. But when we think about IoT, large networks, we will face some significant issues. The first one is this approach is very poor scalable. So one verifier device would have to attest any other prover device within our network, which will end up in quadratic complexity. Another problem is that this scheme is built upon symmetric pre-shared keys, which would require us to install complex key management systems. Another problem is asynchronous communication in pub-sub networks, and the synchronous one that is usually required by traditional remote attestation. So in pub-sub networks, we do not have synchronous communication. And an additional problem is that prover and verifier have to be available the whole time throughout the attestation process, which might be difficult, especially if we think about sleeping devices that go into low power or battery saving modes in order to preserve their durability. And once again, the device heterogeneity might be a limiting factor. To overcome some of these limitations, the so-called collaborative remote attestation schemes emerge, and we classified them into two different categories. The first one being schemes that are considering one verifier and many provers. This means we have one verifier who can attest a whole network of prover devices at once. This is usually done by having some kind of predefined structure, like a tree or a ring structure. The benefit of this, it obviously increases the scalability, but it also has some weaknesses, especially when you think about on-demand attestation. So one verifier is usually not possible to attest a chosen prover device, and only this device, but has to stick to the structure. So for example, if you think about a tree structure, he only can attest the whole tree, or at least one branch of it. This also is an issue when you talk about heterogeneity, as it usually works fine as long as we have the same kind of devices in our networks and we can stick to the predefined structure, but it will make us very unflexible if we want to vary the device types and also maybe have some devices that are not located at the same place throughout their whole durability. And now if we especially think about pub/sub environments, we have like the biggest downfalls of those schemes, as they are not designed to consider asynchronous communication and also do not work for sleeping devices at all. The second category of collaborative remote attestation schemes are the so-called many verifier and many prover schemes. As the name already tells, we do not have one verifier anymore, but we can have many of them, attesting simultaneously many prover devices. Unlike the one verifier, many prover approaches, we do not have to rely on a certain predefined structure, which gives us some benefits, but also has some downfalls, especially when we talk about scalability. The biggest problem here is that the verifiers cannot reuse attestation conducted by other verifiers, as this would require them to trust one another. But, as I already mentioned, we have some benefits from these approaches, as we have obviously easily on-demand attestation, as the verifier does not have to rely on a structure, just can access the prover device and attest it whenever he wants. And it also works much better for heterogeneity, as we can deploy many verifier devices, like for example, one verifier device for every device of IoT device in our network. But once again, when we're coming to pub/sub communication, we have the issue that also those schemes do not work for asynchronous communication and also do not have any consideration regarding sleeping devices. To overcome those limitations, our idea was to create a hybrid approach, which basically merges the two previously discussed categories. But how can we do this? So the key component of our hybrid architecture is a smart contract-based proxy verifier, who has, by the nature of a smart contract, some very useful benefits, as it is always online, it never sleeps, and is therefore always accessible for attestation messages, and it is trustless. So we do not have to put any additional trust assumption apart from the typical blockchain assumptions. So what does this give us now? So the idea is to use this proxy verifier smart contract to attest the verifier devices, and as it is trustless, the verifier can now reuse the attestations conducted by other verifiers, which makes those solutions obviously much more scalable. But unfortunately, instantiating a smart contract with such capabilities isn't really straightforward. So when we were creating this proxy verifier smart contract, we were facing three major technical challenges. So the first one is, by nature, smart contracts are passive entities, which means, unlike the verifier we had before, it cannot proactively trigger the attestation. But we were able to solve this by switching to self-attestation triggered by the IoT devices themselves. A second issue is that smart contracts are public, so everyone can look at them, and this obviously results in no confidentiality, so we cannot save any or store any pre-shared keys in them. To overcome these limitations, we swapped towards public key cryptography for our attestation evidences, And a third issue is because of the poor source of randomness of smart contracts, we cannot actually effectively generate random nonces which are required in order to have a proper replay protection. To overcome this limitation, as we're using blockchain, we can use the blockchain height as a nonce of freshness. So how does all this now come together? Let's have a look at the actual design of SCRAPS. So our system model includes 6 different entities: the manufacturer and its corresponding smart contract, a prover and a verifier device, and the already briefly discussed ProxyVerifier smart contract, and a broker, as we're talking about pub/sub environments. In the first step, the manufacturer who manufactures our prover devices will upload the prover's configuration to its smart contract and also deploys a chosen attestation scheme on the prover device itself. Once the prover is deployed, he just simply registers itself at the ProxyVerifier smart contract and can from there on submit attestation evidences. And whenever an attestation is submitted, the ProxyVerifier will verify them by querying the manufacturer's smart contract and storing the outcome to the blockchain. Now we have the benefit that every verifier can simply query the blockchain or the smart contract and request the results of our attestation evidence with no need of having to actually contact the prover device or even attesting it anymore. To show the capabilities of SCRAPS, we have evaluated it against Legiot, to the best of our knowledge, only state-of-the-art many prover and many verifier attestation scheme with an open source implementation. So the first evaluation we were looking at analyzes the scalability of both systems. While during our testing, SCRAPS did not show any limitations for up to 25,000 devices, Legiot already reached its peak at somewhere around 800 devices and couldn't scale any further. The second evaluation we want to look at deals with the actual benefit of using such a scheme. Here we have to look at the hit percentage as our main performance measure. It gives us the amount of queries for attestation evidences that could be answered by using one of the systems without having to run attestation once again. One could potentially compare it to a cache hit ratio in a cache-based system. Here we once again have the picture that for up to 1,000 devices, both schemes work very well, with SCRAPS being slightly superior. But afterwards, Legiot significantly drops while SCRAPS remains its high capabilities. To wrap things up, we have to look at what we achieved. So first of all, we were able to create a hybrid collaborative remote attestation scheme by merging the previous ones, which allows us to get the benefits of the individual remote attestation categories, but also we do not stick to the limitations of the previous ones before. And also with our ProxyVerifier smart contract, we were able to create the first solution suitable for pub/sub environments. Thanks for attending this talk. I'm really looking forward to a question.